I'm here today with Jeff Anderson, who's helping Spark Microsystems with audio. I'm Frederic Nabki, CTO of Spark Microsystems, and we're going to be discussing audio today. How are you, Jeff?
I'm doing well.
Great. Well, let me start off the discussion by sharing a couple slides to introduce things, and then I'd like you to go, walk us through your measurement results and your data so we can see where Spark technology is on audio. Great. So hopefully you see my screen.
I do.
So essentially, Spark ultra-wideband is the future of short-range wireless networks. We are a technology that has high data rate, low latency, ultra-low power, and is interference robust. So that can be very useful in a slew of applications, from augmented reality to headsets, speakers, human interface devices, and so on. When it comes to audio, we know that wireless usually compromises audio quality due to the use of audio compression codecs, whether it's LC3, LDAC, aptX, whereas our technology is able to send the audio stream uncompressed, essentially the PCM data. So that's what I hope Jeff will be able to show you the detail of with regards to the audio quality that we get when we're able to send the data uncompressed and get the actual performance of a wire through a wireless channel. The other important part of Spark technology is it allows us to send that audio uncompressed at low latency, single-digit milliseconds, and we'll talk about that as well later. And that's also pretty unique of the technology. So the ultra-wideband spectrum, quick primer, is a spectrum from 3.1 to 10.6 gigahertz. It's a worldwide spectrum that's unlicensed, but of course it's regulated. And what's great about it is it gives you access to a lot of bandwidth, and it can coexist with all of the other standards. So fundamentally, our company is bringing to market our second generation transceiver in a couple months, and that transceiver is able to provide 41 megabit per second PHY rate and very low energy consumption, which can rival and beat BLE when it comes to energy efficiency. We have a lot of features with this transceivers. It can do way more than just audio transport, but today we're going to be talking about audio transport. So when we talk about ultra-wideband audio at Spark, we're talking about 96K 24-bit high-quality sound that's uncompressed with low and predictable latency. That's another piece that's important on latency. We want it to be stable and not have jitter on it. And we want to do that at low power so that mobile devices like headsets can make use of the technology. So there's a dilemma in audio. End users want high quality audio. They want essentially the same quality that they get from a good old copper wire, but they don't want to also live with latency of the wireless channels typically, and they'd like to live with no interference issues. So they essentially are saying we want the wire, but they also want mobility. They want to have something that's comfortable, not have to worry about, walking away from their desk with a wire tethered to them. So with BLE or other 2.4 gig radios, you don't get the high quality, you don't get the latency, and you're fairly congested. So there seems to be an impasse here, and Wi-Fi seems on paper to be a great technology to fix that, but unfortunately its latency profile isn't compatible for flat and low latency, and that's due to many reasons we won't dwell on here. And also its power consumption profile isn't really compatible for long battery life headsets or other battery powered devices. One thing we've done at Spark to demonstrate what you can do with ultra-wideband technology using our chipset is create this 3D printed pure tone audio headset demo, which marries ultra-wideband technology from Spark's SR1120 chipset with Bluetooth, so that you get the uncompressed 7 millisecond latency experience at 96K 24-bit. But then when you go very far away beyond the 10 to 15 meter bubble, it graciously goes down to Bluetooth audio so that you can keep the range expectation the same as you would on a BLE headset. So in our view, that's the best of both worlds, where you marry ultra-wideband technology with its capabilities and audio quality and unparalleled latency with the range of Bluetooth when necessary. We've had some customers deploying audio in their products in the last 12 months. Sonus Faber is one where this bookshelf speaker system was released about a year ago. This is again uncompressed, very low latency system on the order, I believe, of 10 milliseconds. So that was a great demonstrator. And more recently, this month, Focal came out with a fairly, I would say, utopic headset speaker system that is clearly best in class when it comes to audio quality. And they're using our technology to transit the signal unimpeded from the master speaker to the coordinated speaker. So essentially, these speakers leverage our technology to send 96K 24-bit audio from one speaker to the other with very predictable and low latency, and more importantly, without any quality impediment. So our technology can be used in a lot of different audio applications, from speakers to headsets to musical instruments that are very latency sensitive, and also microphones where I guess live recordings also care a lot about latency and voice quality. So with that, I'm going to stop sharing, and I'd like to give you, Jeff, the screen so that you can go through your data on how you evaluate our technology with regards to audio quality and latency.
All right. Give me 1 second to get this set up. All right.
Looks good.
Okay. All right. So I'm Jeff Anderson. I had 25 years at Logitech as the Director of Electrical and Acoustical Engineering, as well as Director of Technology Strategy, focused primarily on the audio products at Logitech, and did a lot of research in wireless, Bluetooth, Wi-Fi, and other technologies for speakers, gaming headsets, office communications, and those things. Spent many years doing that, have studied a lot of technologies, have a master's in electrical and computer engineering, and currently I'm an independent consultant and currently helping Spark with their audio initiatives. So what we wanted to do is we wanted to look at the Spark radio system from an audio standpoint. It's one thing to look at the system and stuff bits into it and see that the bits are coming out and as expected, but it's another thing to really look at that and see if they're being recompiled correctly into an audio stream in such a way that there aren't any audio artifacts. Moreover, we wanted to take this opportunity to look at other competing wireless technologies in this space and do a real comparison to what is currently available in the consumer arena for wireless technologies and how Spark stacks up against that. And so the critical factors that for high quality audio wireless, includes high audio quality. Certainly 9624 is a benchmark for the highest quality available these days. But lots of things can do that, as Fred alluded to, in the real benefit to really delivering a good experience, particularly in time-sensitive applications like gaming or sync to video sources and those things, is being able to deliver a high quality undistorted sound also at low latency. So what we did is we did a comparison. We're using a wired connection as our reference, basically a loopback on our test apparatus, and we're comparing LDAC, aptX HD, aptX low latency latency against the Spark ultra-wideband radio system. We also have the aptX standard as part of some of the tests that we did. Our test setup, we had to use a couple of different off-the-shelf modules to complete the full suite. So I'll go through a brief description of what we have for the test setup and what some of the caveats are with the test system we were using and the test apparatus we were using. So the first one here is an off-the-shelf FIIO BTA30 Pro wireless transmitter and receiver pair. This, although the documentation claimed that it supported LDAC at 9624, and you could feed 9624 into the transmitter, the only output I could ever get out of it was 16-bit audio. So there was a limitation there, and so we had to test with what we have. It also supports aptX and aptX HD at 4816. And it also supported SBC at 4816. And so as you can see, we had that hooked into the analyzer through an optical speed-if output for driving the signals into the transmitter, and an optical speed-if input so that we could read the data coming out of the receiver. And then we connect the two with a straight coax. The next system we had, because the prior system didn't support receiving of aptX low latency, we found another module, the Simolio Bluetooth transmitter receiver that supported aptX HD and aptX low latency. And this system supported up to 4824. And so we used that system to do a lot of the aptX HD and aptX low latency testing. It had a very similar test setup as the prior, except we couldn't access the antenna ports with coax. So we just left it at line of sight over the air at about 6 inches spacing. And then finally, the Spark ultra-wideband system was their quasar evaluation kit using the SR1120. And in that system, instead of using optical, we used digital I2S feeding the transmitter, and then digital serial I2S coming out of the receiver back into the audio precision. In all cases, we were using the audio precision in loopback mode as our reference, straight wire reference. So we focused on just a handful of tests that are usually the most revealing of an audio system. I prefer to use FFT measurements because the FFT can really show graphically the kinds of distortions and noise floors that are being injected into a non-ideal system. And we can see that quite readily in the graphs. We are measuring, the first set of data is measuring just pure sine waves so that we can get an accurate THD plus N number. And then we looked at square waves and some multitones to truly exercise the compression and decompression systems of the lossy audio systems. And then finally, we did some latency measurements so that we can compare those as well. All right, so the first graph that we see here is just the loopback reference of the AP system itself. So this is the FFT showing a -1 dBFS at 9624. And we have the spike with no harmonic content, which is what we would expect. For those of you who are familiar with FFT measurements, we are using very small bins. And so that's why the quote unquote noise floor looks artificially low at -180 dB. That's obviously not the true representation of the noise floor for a 24-bit system. But when your bins are quite small, you're not collecting a lot of noise in each bin. So that gives a bit of an explanation as to what you see in the graph. But the real value there is in the actual analyzer FFT or THD plus N measurement value. They're shown on the right. We have both the SINAD and THD plus N level, which delivers very similar numbers. And that is what we would expect from a distortion-free, noise-free system for a 24-bit audio system at about -142 dBFS. That's our loopback. And so we'll continue now to look at what we received from other systems. So in this graph, on the top right, we see LDAC at 9616 compared to the loopback. And as we would expect, because it's only outputting 16-bit audio, we have a requisite increase in noise floor. But for the pure sine signal, the LDAC system really doesn't contribute much in harmonic content other than the degradation in the noise floor. So we're getting pretty much what we would expect. The bottom center graph is the frequency response sweep. It's not entirely flat. There's a little bit of roll off at the low frequency, but it does extend out to 48 kilohertz audio, which is what we would expect. And then the THD plus N sweep versus frequency, again, pretty much represents what we would expect from a 16-bit system. There's a little bit of distortion added at the higher frequencies with LDAC. And the THD plus N level is measuring pretty much what we'd expect. Well, LDAC is a very high quality algorithm, and we would expect it to handle sine waves reasonably well, which it does. aptX, we can start to see some anomalies here. So aptX has a characteristic increase in noise floor. They do noise floor masking of some of their harmonics, which is a common trick in compression algorithms. And so this aptX sweep shows a requisite increase in noise floor, and as represented and shown in the THD plus N measurement, we're seeing about minus 70 dB. We're seeing the roll off because it doesn't extend out to 48K at all. And most interestingly, in the THD plus N versus frequency sweep, we see a lot of anomalies in the frequency response versus THD, as well as some non-periodic signals, which are difficult for the AP to lock into. So these spikes are actually not anomalies in the distortion, but more anomalies in the inability of the AP to actually lock in on that signal, and so it timed out rather than sit there and try to acquire a signal that was unstable. So the way to interpret that is there's a lot of instability in the output signal that sometimes the AP can't lock into. As we move on to aptX HD, we see an improvement in the noise floor, and as represented in the THD plus N, it's minus 81 dBFS. We see a slight improvement in the THD versus frequency, still a few timeouts, but still, not particularly clean graph. As we look at when we jump to a 24-bit system, we see again a slight improvement in the noise floor, but still some anomalies in the frequency response versus THD, with more timeouts presence because of the instability of the sine wave. And aptX low latency, similar. A lot more instability in the signal, which forced AP to time out quite a bit on the frequency response versus THD plus N signal. And then if we look at good old standard Bluetooth SBC, we sort of get the harmonics that are indicative of that lossy algorithm, and then the THD plus N graph there as expected. And again, we get about a minus 68 dBFS for our total THD plus N with the SBC at 4816. Now, when we look at the ultra wideband, we're comparing here the loopback reference with the ultra wideband, and we can see that the ultra wideband is not only delivering full 9624, but we're getting absolutely no harmonic content, no additional noise floor whatsoever. And in fact, in the right-hand side of the screen, we can see that the ultra-wideband was delivering a minus 141 dBFS THD plus N, which is almost identical and probably identical within measurement error to the loopback reference of the system. That's actually pretty phenomenal that we get such a clean signal going through a wireless transmission system and back into the AP. And when we look at the frequency response of the ultra wideband, it is obviously dead flat from 10 to 48 kilohertz of audio, and a pretty much dead flat THD plus N signal result at right at the theoretical limit for 24 bits at 100 minus 140 dB. So the next signal we're going to look at is a square wave at 100 hertz. I have a time domain graph shown here on the right, and with the interpolation off so that we can see the actual samples getting into the AP system. And then on the left is the harmonic content of a square wave. And so that looks pretty much like what we would expect it to look like. Square waves have lots of harmonic content. It's not within scope to explain what square waves are and how they're made, but the nice thing about them is they are full of sine waves, which make them an interesting signal to look at, particularly when we're dealing with lossy algorithms. And so this is a loopback reference. We can see that the AP is putting out and measuring a perfect square wave at 100 hertz and perfect harmonic FFT response. And we'll use that as our reference as we look at how the other systems perform. So the first one we're looking at is LDAC. And so the left-hand side is the FFT and the time domain picture of the square wave. And on the right-hand side, we can see the FFT result coming through the LDAC system and the time domain signal of the square wave. And so we can see that there's lots of noise issues in the FFT, but more interestingly, when we look at the square wave itself, and again, this is only 100 hertz, when we look at the square wave itself, there is a lot of instability, a lot of overshoot, and some attenuation at causing the slopes on the square wave itself. And so we are not getting a clean square wave output out of LDAC at all. And if we jump to aptX at 4816, again, we're seeing some anomalies in the harmonic content as well as a much elevated noise floor. And again, lots of overshoot and distortions in the time domain signal for the square wave. If we look at aptX HD, we get a slightly lower noise floor, but we still get anomalous response in the FFT, and we still have a lot of instability and distortion in the square wave itself as it comes through the system. If we look at aptX HD at 24-bit, similarly, it has some anomalies in the FFT response and even more distortions, which would make sense because aptX HD at 24-bit is trying to cram a lot more data through a Bluetooth pipe. And so even though it's supposed to be higher quality, there's a lot more compression artifacts trying to get that data through. aptX low latency, again, lots more anomalies in the FFT response and quite a bit of distortion and instability, overshoot instability and sloping of the square wave itself for aptX low latency. And then finally, when we look at SBC, SBC looks relatively clean compared to the others, which is interesting, but still has artifacts and sloping and overshoot in the signal response. Then when we look at the ultra-wideband reference to the loopback reference, we can see that they're almost identical. In fact, I would call them identical. The FFT response shows no artifacts, no anomalies in the curve of the response, no additional noise floor, and then the truth is in the time domain graph where that square wave is coming through completely unmolested. All right, and so the next thing we're going to look at here is sort of a custom multi-tone that I had created just to throw something interesting and unique at the system. The DAW I was working with to create this multi-tone has the ability to create a signal called inverted sine waves, which is kind of looks like ocean waves. And I was able to compile a multiplicity of those at 100, 1K, 10K, 20, and 40K just to exercise the bandwidth limit of the system. So this is the loopback reference FFT. Ideally, our system should be able to reproduce that perfectly. But as we see, that's not necessarily the case. So this is what LDAC does to that multi-tone. You can see an elevated noise floor, as well as a lot of distortion and noise artifacts at the higher frequencies. And so anyone who claims they can hear 96K audio would be able to hear these artifacts at the higher frequencies. Certainly not an accurate reproduction of the signal. This is aptX. Again, much higher noise floor at 16-bit and some high artifacts at the higher frequency where it's masking some of the harmonic signals. And you can see many of the harmonics are missing. This is aptX HD at 4816, so slightly better noise floor, but many of the early or later harmonics are missing and masked by the noise, as well as some jitter artifacts there at the fundamental. This is aptX HD at 24-bit, not a whole lot different. This is aptX HD low latency at 24-bit, and it has a slightly different but similar characteristic as the others. And then this is SBC, which has, again, lots of noise and additional anomalies at the high frequency, which is what we all know and love about SBC. And then finally, when we look at the ultra-wideband is reproducing the signal perfectly. There are no additional anomalies in the FFT. There are no additional harmonics or noise floor spikes. It's reproducing that multi-tone perfectly. So finally, we're going to look at the latency measurements. As we can see, for almost all of the Bluetooth variants, with the exception of aptX low latency, we are in that 200 millisecond sort of time arena. aptX low latency comes in at about 33 milliseconds for both 16 and 24. So we can see that outside of aptX low latency, none of these Bluetooth-based algorithms would be acceptable for any sort of real-time audio, anything that needs to be synced to video or music production, where we need sync or gaming. The aptX low latency is 33 milliseconds, and that's arguable. People will argue whether that's good enough for gaming or not. There are lots of studies who say no, it's not. And even at 33 milliseconds, music production, say an IEM for drums, 33 milliseconds would be noticeable, or a feedback monitor for podcasting, 33 seconds would be more than noticeable. When we look at the ultra-wideband, it's coming in at 6.7 milliseconds, which is phenomenal. And so not much to say there other than you get all of that audio performance and an almost inaudible latency for sync and for music production and gaming. That's pretty amazing that the Spark ultra-wideband system can do that. All right. So in conclusion, the ultra-wideband wireless audio transceiver demonstrates superior performance in delivering high-resolution lossless audio with latencies consistently below 7 milliseconds and a system that is capable of reaching less than 5 milliseconds. A comprehensive assessment using ultra-wideband enabled USB dongle and headset reference design confirm exceptional audio quality comparable to a wired connection. The ultra-wideband transceiver outperforms Bluetooth codecs, namely LDAC, aptX, HD, aptX low latency, which exhibit elevated noise floors and latency issues, compromising audio quality. Latency measurements highlight ultra-wideband's advantages for real-time applications, achieving sub-7 millisecond latencies compared to the other technologies such as LDAC and aptX, which are in excess of 200 milliseconds, and aptX low latency at 30 milliseconds. So the ultra-wideband transceiver is positioned as a leading solution for high-resolution wireless audio applications due to its high fidelity and minimal latency. And thank you very much.
Well, thank you, Jeff. That was a lot of information and data, and hopefully, you know, the audio experts that have been listening have been following, because from what I understood in layman terms, you know, a good old audio cable will probably do better than all of these compressors. And if you want to do this wirelessly, Spark can do it and at low latency. I guess that's the nutshell message.
That is the nutshell. It's an incredible system that something I've never seen before in all my years of doing consumer wireless audio products, and definitely an exciting step function in our industry.
Right. Well, thank you, Jeff. Coming from you, it means a lot, and I'm sure the Spark team will be, quite happy to hear that from you. So thank you very much. And with that, we'll call it a day. Thanks, Jeff.
Thank you.